Hi. How many of you have been to an AirSpike meetup? Seen AirSpike in a meetup before? Yeah, you raise your hand. Oh, a lot of new faces. Great, glad to see so many new people. So I'm going to show you a presentation that I've given a few times before. I've given it in New York at Database Month. I gave it at the Findever conference a few weeks ago in San Francisco. And it's meant to show you what we've been seeing at Aerospike in some financial services and fraud use cases. So I can't talk about the specifics of individual customer engagements. How are we doing back there, Lauren? Working on it. Lauren's working on it. But so I can't tell you the specifics about individual customers, use cases, because it's all covered by NDAs. But Aerospike does now have several different active POCs and deployments with a few financial services cases in this area and in this use case. So I think you'll be interested to see what's happening with this. Let's first talk for a second about Aerospike history, since there's a few of you for whom this is Aerospike's first engagement. So Aerospike as a company has been around since 2009. That's when we were writing the original prototype code, myself and my co-founder, who's back over there somewhere. We got the first round of funding with Alsop Louis, a fairly small boutique firm providing seed funding in 2011. Started growing the company, launching it, adding new features, open sourcing in 2014, and we're stepping from our traditional ad tech use cases into financial services and telecom primarily. Those are two different verticals that have an insatiable need for speed. So part of what I'm going to present today is a move from SQL in the real-time area to NoSQL, and the kind of change that that requires in mindset, but what you can also start accomplishing with NoSQL. So we saw at Aerospike, I saw this first with our ad tech customers. If you think about the ecosystem of ad tech, what's happening in ad tech is these guys are needing to take in an ad request, use app servers that are running their particular kind of math and their optimization engines, but they need to do a few database requests inline as part of the real-time request to make a decision about what a given impression is worth and how much to bid on the advertising exchanges. In order to do so, of course, they didn't use SQL. Even in 2008, 2009, leading-edge companies would use their own key value stores, they'd use purpose-built object stores, or they'd use a system like Aerospike. And that was the first use cases we found. Of course, they would always have really huge data systems doing the true analytics using not only systems like HBase Hadoop, but Vertica, for example, very, very popular within the ad tech communities. They even often have purpose-built SQL and query engines. But you still need something on the front edge to actually solve the millisecond by millisecond requests coming in to actually serve ads. And that's what we found. And what I'll show you is that this new strategy relies on putting your math and your calculations in an app server. So instead of having an app server write SQL, and then the SQL engine then parsing it, having a lot of CPU, and then creating I/O requests out to a storage layer, instead you've really now got only two systems. You've got a CPU-heavy system with very, very little storage, and then you have a database layer, which is direct attach and includes storage inside it. So going from even a 4-layer model to a 2-layer model. So within Aerospike, we've been satisfying mostly ad tech companies and internet companies from mobile advertising, search gaming, many of these areas. Blue Kai, one of our largest customers, you may know, they're a Sunnyvale company. They were acquired by Oracle as part of Oracle Marketing Cloud and is one of our largest customers. So we've got some new benchmarks out recently. This was a benchmark that we ran nearly a year ago. Those of you who remember Google Compute with Cassandra did a test that showed 1 million writes per second. If you remember that one, 1 million writes per second on Cassandra. They required 300 nodes to actually compute that. We did a benchmark showing 50 nodes about 9 months ago. But just yesterday, that benchmark was redone by a Google Compute VIP called Lynn Langett, and she showed the same result in 20 nodes. So one thing we know is for those use cases where you're using Cassandra for key value, as opposed to time series, Aerospike can be a really, really effective choice. So literally today, well, literally, not literally, because it was literally yesterday, we've got new benchmark results, this Google Cloud Platform blog entry. So this is on Google Cloud Platform's blog if you want to go see it. We showed some Lynn validated benchmark results with some pretty impressive numbers. Now that's on RAM in Google Compute Engine. And also just yesterday, a company called Demartech showed for this same fraud use case I'm going to present to you today, a pretty interesting Dell Samsung SSD configuration that's capable of 1 million reads per second, 400,000 writes per second on 4 servers using NVMe SSDs. So 4 servers for that kind of horsepower. That's what you can get on bare metal with Aerospike. If you're used to the kind of performance of Redis, this was also Lynn Langett's work. She showed that Aerospike is a little bit faster when you're running in a sharded mode than Redis, but a lot faster if you don't bother sharding. So a lot of people will run Redis with only 1 shard on a 12-node system, waste a lot of CPU, whereas Aerospike is multi-threaded. I'll just spend for a minute about the architecture of Aerospike for those of you who are new before going on to the interesting stuff of the use case. So Aerospike is a clustered database, and so the database server is separate. So just like a standard NoSQL system, there's a network hop between your application server in that architecture I was saying. Compute is separated from data by a network hop, allowing each one to scale separately. We have different client libraries, a lot of different client libraries to support the different kind of mathematical systems you might be using. And Aerospike itself is a C-based, Linux-based server binary. So you'd install that on a set of Linux servers, you would configure them all to talk to each other, and they would cluster up. That software has in it the failure and redundancy system. So even though you can hook it up to a system like Mesos or Docker or anything else or Swarm, it's doing its own checking and its own system underneath the covers. So one way to think about it is if you know RocksDB out of Facebook, RocksDB is a library and it has no distribution system to actually do clustering. Facebook has an internal system, I think it's called Fuzz, that actually has clustering above RocksDB. What Aerospike is like is the Flash-oriented RocksDB with the entire clustering system of Fuzz, which they haven't open sourced because that kind of distribution system is actually part of their core intellectual IP. With Aerospike, you get all of that. So that's the core architecture. And we can add, if there's anyone interested about it, I want to move on to this cool fraud detection stuff, but we can talk about some of the architecture later. So what's been happening within these companies that are doing payment processing in financial services? A payment processor, that's that guy in financial services who actually takes a transaction. Hey, here's the credit card number, here's the IP address, here's whatever information I've got. I've got swipe, I've got card, it's an online transaction, I don't have any of that, maybe I have IP address. I've got some set of information about the transaction, and I have to record that, and I have to decide whether to pay or not. A lot of old school fraud detection was done offline. So you might get a transaction that doesn't actually get debited or gets questioned after the payment occurs or the merchandise gets purchased. Online fraud detection attempts to go one step further, inline fraud detection attempts to use a window of about 150 milliseconds to determine while the transaction is happening whether it's fraudulent or not and block the transaction in flight. So if you think about that problem, it is kind of like that ad tech problem where you're going to use as much information as possible in line right now within a few milliseconds, in their case 100 milliseconds, to determine the likelihood of fraud and decide whether to ask for more information during the transaction or to in fact block it completely. So the way that this had been done up until the NoSQL revolution was to use rules engines. Rules engines are, I would call them fairly, naive is maybe too harsh a word, but fairly simplistic technology because the number of rules that you can create is fairly limited and you express them in a fairly limited way. You would say something like the classic example, if this transaction and the next transactions are more than 100 miles apart and more than an hour apart, the likelihood of fraud goes up, right? So these rules would be pretty generic. Subtract this from this, this distance from that distance, and if that is greater or less than a particular value, increase the fraud score. So, compared to today's math and what we have in big data, that sounds pretty simplistic. And yet that's what a lot of the systems are still using. Rules are often generated on a monthly or even yearly basis. That's the rules themselves. And then applied to the last data for a given account over the last weeks or months. And that's really the state of the art right now. If you go and talk to Visa, they primarily have systems that are using these rules engines, even though many companies are starting to switch to something new. So what happened was these guys said, you know what? We need to stop using these simplistic rules and stop generating SQL. When you're trying to talk about, SQL is a great system when you're trying to model a business system, and that business system is really, you know what the transactional relationships are. You know that there's a relationship between the debiting account and the adding account, things like that. When you're dealing with these kinds of business systems, modeling them in SQL, the relational algebra gives you a huge amount of power to model that. However, that SQL often takes months, if not years, to get right and to properly express the business relationships. What you're trying to do in fraud is find bad guys now. And you're trying to get new algorithms online to catch those guys as fast as possible. You may have detected a new string of fraudulent transactions a few hours ago and a new kind of attack. And you need to get some code online as fast as possible to start preventing fraud. And that's not really what SQL's great at, right? So what we've got now is a system where you want to use something like a decision engine. And that's this kind of math I'll go into, and I'll go into that in some depth. And you want to have a database that's not really a compute engine, but is much closer to a storage engine and is capable of billions of objects and millions of transactions per second. Let's go through the math for a second, because I think it'll make it a little more real. A lot of these payment systems, how many payments are there in North America for a large-scale payment system? There's only a few hundred per second. Maybe there's thousands. And you think, well, thousands of database lookups per second, that's not that big a deal. An in-memory NoSQL system, an in-memory MySQL system can handle a couple thousand per second. But what's interesting about the pattern I'll show you is you might want to look at thousands of data elements, literally thousands, in order to make a decision. So once you start adding up 500 of these times 5,000 of those, you're getting into the millions of transactions per second to make a decision. You'd like this data path portion to complete in tens of milliseconds so that you can have part of your 100 to 150 millisecond budget still left to actually compute fraud scores and results. So what are the algorithms that are being used instead of these classic rules engines? Well, they fall in line with machine learning. That's probably the best way to think about it. Again, I can't go into some of the algorithms and discussions that I've heard about. I'm going to give you an example. But what we know about machine learning, for those of you, I'm kind of a beginner at it. I haven't used it in anger myself. But we have done some research here at Aerospike, for example, trying to predict using the Caltrans real-time traffic data. You've seen the sensors in the roads. We sponsored some research in being able to tell an accident from a standard slowdown in real time using machine learning. And which features, that's the machine learning term, right? Which features and how much data per feature is required to make an accurate model according to which machine learning system. So that's the kind of problem that is also being applied in these fraud scoring systems now. So you've got a lot of features. And you'll find over time that some features are more valuable and some features are less valuable. Item sold is actually a pretty interesting one from what I read. People who go and buy 5 identical Rolexes, all of the exact same type and exact same size, that's a suspicious transaction because most people don't buy 5 of them at a time, and they don't have 5 arms, and they're not. It's not a wedding party where they're giving them to their 5 brides, the 5 groomsmen or something like that. It's really rare. Yet for fraud, that is a common pattern of buying Rolexes because those can be converted very quickly and easily into dollars. So things like item sold, price of item, time of day. You may find that a particular attack or attacker fraudulently is going from either IP address ranges, time of day, and all of that's going to shift. You're going to find, based on new attacks, different patterns that are occurring. Recent data, that's part of what's necessary, as well as access to different code libraries. So let's walk through a very specific example, and I think you'll see how the NoSQL pattern applies to this kind of use. Let's take IP addresses. You might very well find that an IP address is an example of a machine learning feature that's really powerful. That recent traffic, maybe not even transactional traffic, can be applied to solving transactional problems. Now, as an aside, your mileage may vary. I'm not a lawyer, and the use of certain data within transaction processing is illegal under US law. So don't go and take this that you should go do this, because as far as I know, it might be illegal to actually use things like social data to determine fraud scores and blocks transactions. There was a Fair Trade Commission thing about a year ago that went into some of that. So I'm not saying that that's what people are doing, and I'm not saying that you should do it. It might be illegal. This is an example. So if you had IP addresses and you really did want to look at the amount of recent network traffic to and from a given IP address, well, you've got a modest number of objects, a modest number of IP addresses. 2 to 4 billion items to track by internet standards is actually not that bad. What we see at Aerospike in North American advertising is most large networks are tracking between 1 and 10 billion cookies at any given time. So this number of IP addresses and having an object per IP address is a tractable problem that you can do with very few servers. If you go look at that Demand Tech paper, they were talking about 2 billion objects on four servers with millions of transactions per second. So this is all very reasonable right now. Now, you don't know the number of networks. You do know the number of IP addresses, and sometimes your fraud scores will be based on a network, like a old-style Class C, sometimes not. Now, in IPv6, these are all IPv4, obviously. IPv6, the patterns are actually kind of similar. I've just started researching that because you still do have the same number of endpoints, and you still do have essentially NAT systems currently for all the mobile providers, and you do tend to have a home with one even IPv6 address. So the best thing to think about is that in IPv6 there aren't networks anymore. There are more individual IP addresses, and the idea of trying to use nearby IP addresses might be less powerful in v6. Other than that, the idea of having these addresses pretty much follows even in IPv6. So you need some recent behavior. So how would you consider doing this in a relational implementation if you were just kind of doing it the obvious way? Well, you'd probably have a start IP address and an end IP address, and your big data Hadoop system is generating a fraud score based on recent data, right? And maybe you've got a Spark system that can do quick turns and can actually chunk out new information every hour. Maybe you've got an older, larger Hadoop system. They're doing larger calculations, and this is a 24-hour fraud score. Still not that bad. You're going to have a table that looks like this. Your select is going to look kind of like that. Again, this is naive SQL. There's a lot of ways to optimize this. Now, the problem with this is you're doing a range lookup. Range lookups are inherently slow. It's not a key value lookup. Anything with a range starts looking at 5 to 10 milliseconds, even on an in-memory system, and not the sub-millisecond you should get in a key value system. But it gets even worse, because what you really want to do is you want to have recent behaviors at an IP address. So for an individual IP address, did they issue a transaction? Did they issue a tweet? What did that tweet say? Those kinds of things. Again, it may be illegal to use social media to do financial services transactions. Take this as an example. It's really kind of a cool example, right? So if one guy tweets out, I have your watches, please pick up my fraudulent watches at 10 p.m., and then they go buy some watches, you might think there's a correlation, but that's illegal. Okay, so how would you do this in SQL? Well, what you would tend to do is create a table where there is a separate record for each individual behavioral point, right? So you would have a table that looks kind of like this. Well, now you're in real trouble because your lookup is going to look something like this, where you're going to take timestamps for recent behavior to be able to age them out, and you're still going to do this kind of select, so you're doing a two-part where clause. Not only that, you've now got a table that isn't just the number of IP addresses, it's the number of behaviors you're taking in. So this table will probably look at, 100 billion rows, something like that, and you're going to be doing these kinds of range query lookups, and you're going to have to go call your DBAs. You're going to have to find out which version of SQL you're using, what's my most correct index. Should I use, say, partitioning to try to bring data together because I'm going to be looking at a particular IP address. There's a whole bunch of DBA tricks to try to make this go fast. So it's possible, but you better call your DBAs and know exactly what you're doing with SQL. You're still going to need that system where you've got besides your load balancer, you've got an application server generating the SQL, a SQL system actually doing a bunch of CPU-intensive work to traverse the indexes, as well as a storage system that can actually pull whatever you're doing. So what would this pattern look like if you were programming it for a NoSQL system? Well, the first thing you're going to do is you're going to start embedding some real-world knowledge in your data system. And you talk to any SQL person, and they're going to say, that's an awful idea. We're really trying to create an abstract representation. We're not going to embed any special purpose knowledge in the data structures. And that's part of the difference in philosophy between SQL guys and NoSQL guys, in my experience, is NoSQL guys are going to say, yeah, but it's going to go really fast if we embed a little bit of business knowledge, if we embed a little bit of our application knowledge. And again, I would generally say, if you're doing business logic, if you're doing a query or a data structure that is going to be decades in lifespan, you might want to stick with SQL. If you're trying to find some bad guys now, that's a great choice for NoSQL. So how would you do this? Well, the first thing I would probably do is I would key on class C addresses. And I would use that as essentially a denormalization step, so that if I wanted to look at a particular network range, I could do a first fetch, and I could pull a given IP address range. Now, there's only 24 million of those, and then get a list of network objects. That's going to mean I don't have to do a range query, even for arbitrary pieces of an IP address system. Right? In the other example, I had to do that. I always ended up doing a range query, and I had specific IP addresses. So I'm going to do a little bit of a hack here, and I'm going to embed some special purpose knowledge in my data structure. So I'm going to take a key and look up a list. Now, you can, in SQL, use lists as targets and do all of this stuff, but NoSQL is really purpose-built for this kind of thing and supports lists as data elements. Now, the second thing I'm going to do is I'm going to primary key, essentially, off of these IDs, and that will get me the kinds of scores that I would use in the other system. So in this kind of data architecture, I'm doing 2 network round trips. Sounds more expensive, except these are scalable, highly parallel, embarrassingly parallel requests, and not range queries, which are inherently the kind of data structure that is very, very hard to parallelize and very hard to cluster. That's the difference. Let's go one step further and talk about how you would do something like a list of recent behavior for a given IP address. So not only would you have a score, well, in the NoSQL world, the model you would use is you would tend to use something that looks more like a document in that sense, or at the very least, just a list of recent behaviors. So imagine that you're in Redis and you want to use a Redis list. Imagine you're in Mongo and you want to use a capped collection, something like that. The kind of, actually, this isn't a capped collection in Mongo, but I'll take that back. In any case, the ability to embed a list and insert something onto the end of a list makes this system a much more tractable problem, because inserts, well, I simply go to which network address, and then I pop it onto the end of the list. It's an embarrassingly parallel. I find this one object, I find it on the server in question, and I can go to town on that particular operation in a parallel way. Inserts become highly scalable. I still have my 2 network requests, and I have a little multiplicative case, right? I go and I get this list, and then I'm going to have to get a bunch of things here in order to make this happen. On the other hand, remember, I had all the kinds of transactions that a NoSQL system is capable of doing. So instead of building a SQL database that's capable of hundreds of thousands of requests per second, you can build systems with millions of transactions per server. They're simpler transactions, but if your data fits in this kind of model, you can get a much more cost-effective solution. And so I know what you're going to say, because everyone says it. I could do it in SQL. And that's true, right? You go look at Postgres. Postgres has a really nice system for using lists. It allows you to do in-database functions, all that kind of stuff. But it's still kind of hard, right? You still have the problem, and you still have the fact that NoSQL is much, much faster than the corresponding SQL systems and cluster a heck of a lot better. Now, one of the factors that you've got to deal with when you're trying to use this pattern in a financial services scenario is you're often wanting to use something like machine learning libraries. I'm particularly fond of Datto. That's what we used in our traffic system. It's another company funded by NEA. They used to be called GraphLab. And the Datto libraries don't create SQL. And if you're using Spark and you're using an RDD, those things don't generate SQL as part of their real time. They generate RDD requests. Now, you can map them into SQL, right? You can still do it. There is a path to doing it, but you're going to be losing speed every single time you do it. So these kinds of application server libraries, these cutting-edge libraries, don't emit SQL. They're not optimized to generate high-performance SQL. So we think really, I'm finding that this kind of NoSQL environment is better suited for the most cutting-edge libraries. What we've also found at Aerospike in this pattern is support for a lot of languages is important, and really being highly polyglot. Because what you're really doing, going back to this picture, is you've got this compute tier, and the question then is, well, what's that compute tier? What's the best language for this particular problem? Is this a Go-style compute problem? Is this C with MATLAB? Is this a PHP problem? Is this a Python problem? You really want to have a well-optimized library for each one of the languages, which is kind of hard. But at Aerospike, we found that to be a necessary part. We can't just be a database company. We have to be a client technology company to make sure all of these libraries are hyper-optimized for not only performance, but also for idiomatic use. And if you think our library in some of these is not good enough, come see us. We're hiring, especially on the client team. So we're always looking for people who work really well and know the internals of individual languages so that we can make sure that those are not only idiomatic, but proper across all the versions of a given library and language. So let me talk to you for a moment about Flash, because that's a key component about the using this kind of database and this kind of use case in financial services. What I've found across multiple engagements in this industry is this profile is what everyone's asking for. They're asking for tens of billions of objects, hundreds of terabytes, millions of transactions per second. The same piece of math I mentioned, 50 milliseconds per 5,000 queries is kind of close, and domain replication. Because all of these cases are literally mission critical. If the fraud system goes down, then, well, either they're exposed or they end up stopping transactions. Either way, that's a pretty awful problem. So this core idea, I'm not saying who's doing what, but it's a use case and a size we've been exposed to multiple times. Now those might be, like I said, these features. They might be IP addresses. They might be different retailers. They might be SKUs within different companies. They might be different retailer sources. If you have, let's say, even internet cookie information, you could be using something like that. But it all nets out at about the same place. So the question is, what's the way that you can actually reach hundreds of terabytes, millions of transactions per second over that particular case? Now, if you're using a pure RAM database, this would look like a pretty expensive proposition. And the problem really isn't the number of chips to get here, right? Because chips have gotten cheaper and cheaper and cheaper. And the amount of money that you pay for a given terabyte of DRAM has gotten kind of reasonable. Now, the density, the overall density when you count in the CPUs and all that is still kind of high. But it turns out that the real problem is power. And power is not getting any cheaper. So what we found at Aerospike is that this is a case, even though as an in-memory database, we support RAM and NAND flash, we have found that this particular problem really, really works with NAND flash. You have to have fast flash. So this is a particular generation and a benchmark that we did with Intel, where a single server, we can do 1 million transactions per second on one server. Now that was a server with 4 Intel P3700s and 1.6 terabytes, I think, per server. So that's a little small. I'll go through some example configurations. But this is what's possible today. Now, one thing that we found at Aerospike is there's been such a big difference generation to generation and year to year within NAND flash that a lot of people still have questions about whether NAND is safe, whether NAND is effective, whether it can be used in data center environments. And so what we did was we created a benchmark in 2011 that was a simple piece of C code. It could be ported anywhere, could run in almost any environment. I don't think we've run it on ARM processors or too far outside of Linux, but it was the simplest case we could do to create a benchmark. The most important part about this benchmark is it has reads and writes at the same time. Most benchmarks, and you'll even see that in some of our benchmarks as a database, do a bunch of reads or they do a bunch of writes. And they don't do them both at the same time. And that, it turns out, is one of the biggest challenges of flash. So in the next slide, I'll show you some devices and how things have changed over the years. And what you'll see is numbers that are much lower than the quoted numbers of a lot of devices. The reason for that is because when you're doing internet behavior prediction, you need to take recent writes. You can't stop the world and ETL your data in like you would have in some of the old systems, right? Instead, you need to be predicting behavior now, doing fraud detection now, but also taking all of those writes in your workload at the same time. And for that, that's always a challenge in database environments. Many databases are read optimized or write optimized, or at the very least, they don't like you mixing up your reads or your writes. But Flash is just about the same thing and for about the same reasons. Flash is good at reading and it's good at writing. When it's doing writing, it's doing essentially log-based collection in order to apply all those writes to a write block. And when it's doing reads, it's banging on bits and pieces sort of all over the system with their controller. And so what's important to know when you're choosing a flash solution where latency and SLAs is critical is how a particular read SLA is affected by write load. That's why we created this benchmark, and why we also found you had to run the benchmark for a lot of time. There's a lot of devices out there where there's a curve, where it looks great for an hour or 2 hours or 4 hours or 7 hours, and then you start running into one of the magical limits. Many devices have them. So we'll go through and sort of talk about some of the different years and different times within Flash. What we found sort of in the 2001 to 2013 phase was that the problem in Flash controllers of building an effective controller was really hard. It's still really hard. And the fundamental problem is what's called the FTL, the physical to logical translation map. That's what takes a block number at the interface level and finds exactly which flash device, maybe it's even spread over a couple of them, and does a logical to physical, I got it backwards. Well, you call it FTL, physical to logical. So you're taking a block device and actually finding a true physical address. That FTL table, it's in motion as you're doing writes. You have to take write locks and read locks inside the device. And it's been a very tricky piece of code to do historically, and ends up being the problem when you start doing more and more writes at higher and higher velocities, and you don't let up. The way to think about these devices is there's a garbage collector inside. And what we know about garbage collectors is, well, it's all good for a while, and then it all goes to shit for a while, right? That's the nature of garbage. You got to go clean out the garbage. As an aside, I don't know if you guys have seen recent research into why we sleep. And I was just hearing this morning on the radio, that that's one of the reasons why we sleep is garbage collection among the cells. And you actually have to take out the trash in terms of byproducts in cells in our brain. And well, the question is, well, why don't you do that all the time, continually? Well, then you don't think so well. It's better to have a system that thinks really well for 16 hours and shuts down for 8 than to have a system that is steady across the entire time. Now at Aerospike, we've built a system where garbage collection is continuous, and these devices also have to work in continuous garbage collection systems. If you do let a device just sit there powered up for a period of time, it tends to collect garbage if you don't write to it, and that disturbs the test results. So you have to run the test results with steady load, and that actually starts pushing the garbage collector, and you start seeing the real world implications. So back in, let's say 2011, when, I think it was mid-2011 when the 320 came out, that was one of our drives of choice. What we found in general is that the larger manufacturers have had the capability to spend more on their controllers because it's a hard problem. And we didn't end up, we probably had some Sandforce controllers from that period in the field with our customers, but they were rare. And in general, you needed more of them and they could take less load than devices, controllers that were built by an individual manufacturer and mated with the technology of a particular piece of NAND technology. So we tended to find these are Intel drives. This is a Micron drive, so Micron controller using Micron NAND from Micron's foundries. Same thing, the Crucial is a Micron drive. This is a Samsung drive as well as an Intel drive. Those were the highest quality controllers by and large. Cases where you had, for example, the IO Drive 2, the numbers on that in 2011 were plausible compared to the Intel 320. But at a much, much higher markup. So people who I talk to tend to say, oh, well, you know, those Fusion IO drives from back in the day were pretty fast. And it's like, yeah, they were pretty fast, but we found that rarely did they, the premium that they were charged actually make sense. Now, if you're running these under a SQL database, you'll see a different, somewhat of a different story, because the folks at Fusion IO really made a point of optimizing their patterns for MySQL in specific and Oracle in specific. So that's a little bit different, and I could go into detail about architectural issues and CPU stealing and bus stealing, which is done by some devices and not others. This was sort of a weirder time, I would say. Whereas these days, as we're getting into devices with more standardization, in 2013, we really saw the benefits of what I call wide SATA. And so wide SATA is a deployment characteristic where you take usually 22 to 24 SATA drives. You'll probably put 3 controllers behind it. Each one of those have PCIe drives. And so since you've got 24 devices, SATA is not really being pushed that hard per device. And if you have a server database software that will spread the load correctly, you can actually get some very, very impressive I/O numbers out of it. So that's what we tended to recommend and see in our installed base sort of through the last few years. What we've seen just recently is, and we saw then some really great PCIe implementations, but some of them had these quirks, like Fusion IO's bus sharing technology, where it might work in some cases and not in other cases. So Micron Drives in specific in the 2013 time frame were doing some great things at the controller layer that we didn't see other manufacturers doing, and they showed really well on our benchmarks. This kind of number at what we called 150x, which is 300,000 read per second per device, is still one of the fastest results we've ever had. Now, they were, let's call it cheating. They were using not NAND, they were using SLC technology instead of MLC technology. It's one of the last drives that available that did that, and thus that's one of the reasons it did well in our test, but did it at a very high price point. This drive's now end-of-lifed, so you can't buy it. Well, you might be able to buy it, but you won't be able to buy it for long. Since then, everything's gone to MLC, and so we're seeing much more attractive price points within the NVMe category at things like $2 a gig, And you're seeing speeds in the range of some of those devices. So now we're in 2015, and NVMe has finally happened. The results that I was showing you from the Datec paper and from some of our, from that Intel category are all on NVMe drives. So NVMe is really, it's like PCIe in its transport, but it has the added layer of an actual storage protocol on top of it. That's a simplification. There's some people back there who know far more than I do. Is that roughly correct, Arnie? Yeah, okay. I'll get a yeah there. So one way to think about it is back in 2013, there were people doing PCIe, but they were using their own bus protocols, and there was a wide variation. I remember talking to a Micron guy about the exact bus efficiency of some of the Fusion IO systems versus their systems, and how proud they were that there was 50 bus round trips versus 5 bus round trips for theirs, et cetera, et cetera. All of that's kind of smoothed out a little bit with NVMe, but the real benefit is we have a single driver stack. So within Linux, there's now an NVMe driver, everyone can pound on it, and everyone can improve it. Whereas back then, there were really you had to use the specific driver for a specific network card, which might have been extraordinarily well engineered or extraordinarily poorly engineered, depending on the exact generation. So we're getting it to a point of more standardization within the NAND category and more repeatable results, but also higher results. Some people ask me about NAND reliability. Is NAND reliable enough to use? What I'll tell you is that over our customer base, which is a lot of customers and a lot of drives, when you stick to the major manufacturers, you will see very reasonable drive lifetimes. You will see quoted lifetimes matching the lifetimes in the field. If Intel says it's 3 drive writes per day, it's probably 3 drive writes per day or a little better. And again, once you get after 2011. Before 2011, things were pretty lousy, but any drives that you buy now from major manufacturers, we found to be extraordinarily reliable and tend to be more reliable than rotational disks in the same kinds of systems. So yeah, they fail occasionally, but not a lot. You do need hot standbys, just like you would in a rotational system. And the new advent of NVMe systems with front panel attach really help with all of that. So you still do have fails, but they're not so bad. So what are the kinds of systems that you could buy to do this kind of stuff? So if you're doing in chassis, just sort of took this from a price list recently. This was that P3700 system that Intel benchmarked with, where those are in chassis cards, 4 of these 1.6 drives, and $2 per gigabyte, million IOPS per server. Now, if you remember back about 10 minutes when I was showing you the profile of those ad tech use cases, this is actually more IOPS than you need, because we probably only need 3 IOPS, and this is only 6 terabytes. So getting to hundreds of terabytes, you're kind of overbuying on your IOPS. And that's the discussion we have to have with almost every customer. They say, well, how many IOPS? Well, how much do you want to pay? So even though you're paying about $2 per gigabyte, you're getting a little more IOPS than you need, and you can probably buy a drive that's actually a little slower and save a little bit of money, where a little bit of money might be $500,000. So another example here from the wide SATA configurations, these are using things like the 720XD. Those of you who've used them, they've got the 24 front panel SATA drives. You can front panel slot them, and they're closer to $1 per gig, but only get you 200,000 IOPS in a 20T package as opposed to a 6T package. So this is an example of a configuration where you're getting a lot fewer IOPS. On the other hand, maybe you didn't need that many, and you're getting 20T per device, and it's starting to look like a really tractable solution to get to hundreds of T. So AirSpike's a company that's had a lot of experience with these kind of flash use cases, a lot of experience helping companies build NoSQL, and take sort of relational data models to NoSQL in the cases where it makes sense. We've built multi-million TPS clusters, helped our customers do that. We're just a software company, and actually achieved 5 nines reliability in some customers. I went back to our longest running cluster. As far as I know, there's only been a 5-minute outage. I think that 5 minutes was a Monday morning at about 9 a.m. Pacific, because I wrote the line of code that caused it. I missed a free, and we couldn't catch up. Usually the system's very reliable. And really, I'm very excited about this use of NoSQL. It's not really about NoSQL versus SQL, but really trying to find the case that makes sense. And cases where you're doing this richer application environment, where you're using more aggressive math, you're giving developers the language that is appropriate for their technology problem, really creates a completely different deployment pattern than the classic enterprise. What's exciting to me is the classic enterprises that we've seen that are interested in making this trade-off and are, for some use cases, don't want to generate SQL. They want to have their application programmers program something that they eventually find to be simpler when you go through that model change of, oh, I don't have to use a table, I don't have to use a range query, I can just go get that object and I can do it a lot faster. So hopefully that's given you some new ideas for the technology problems you're facing if you're applying machine learning to a particular new use case. And I'm pretty excited about it. So that's applying NoSQL to financial services. So, questions?
It did come late, so I'm not sure if I missed something. So what would be the use case in case of financial industry? Is it like trading?
This use case I talked about was fraud within payment processing.
Okay. And do you handle like one of your use cases as a streaming data? I mean,
this is all about streaming data.
okay. What about if I have data from all the US people? I have the metadata. Can I quickly find out my terrorist?
I think I'm going to have to probably go back and say watch the video for the parts you missed. Yes, we went through a bunch of that stuff. Okay. And sure, it can be used in general for any kind of behavioral. It's a pattern that we saw first in ad tech and is now being applied by a variety of cases, including telco companies as well. Yes, but thanks for breaking the ice, sir.
So in the examples you gave, can you comment on the usage of secondary index? Is that like you have to use it? Or
you don't have to use it.
you don't have it?
Correct. So that's sort of the most interesting point is what I'm finding with these guys is there's almost always a way to decompose your problem into a series of primary key lookups, a series of key value lookups, and avoid any form of range query. And if you do that, you will have a faster system with any database. And that's the core idea of what's happening here, is less processing in the database and using the database more as a storage layer with key value lookups. Any clustered system will go faster if you can decompose your problem into key value.
But then effectively, you need twice the storage. Isn't that true?
Whenever you're in a distributed system, regardless of the indexing system, if you want that kind of reliability, you want HA, you want 2 copies.
All right. Thank you.
Yes? Sorry, back there in the blue.
Have multiple workloads running on a single SSD, how can you provide deterministic SLOs?
The short answer is don't do that. Whenever you have any shared component, you're going to have a chance for conflict between the workloads. And that comes from the bus that's in the networking subsystem, that's in your router, that's in your top-of-rack switches. It's everywhere. So when you're talking about really measuring 99% latency, you probably don't want any shared components. Now that being said, there are some what I consider QoS strategies being developed by different storage vendors. But I'm suspicious of them until I see them, because even in those cases, there are shared components in the devices themselves.
AirSpike does not have the intelligence to use those QoS from the controllers?
We have not found that to be effective yet.
Really good information, and thanks for setting up this meetup. Really appreciate you hosting this. I guess my question is, I noticed there was a lot of SQL versus NoSQL comparison in your presentation. Does that mean that you're seeing a lot of the SQL versus NoSQL argument during your sales cycles?
Yes.
My second part is then, who are your top competitors?
Yes, I'm absolutely seeing a lot of conversations still that revolve around SQL versus NoSQL. In one particular engagement, it was clear that we had a senior architect who understood the power of sticking to primary key and key value. And then it seemed like he was using us as a proponent to go in front of multiple different groups. And there'd usually be a guy there who would say, but I still have, where's my SQL? I don't know what to do. And we have a couple great sales engineers and who sort of very patiently go, no, no, really, you can just use the object. You can just use the object. But where's my table? No, where's my range query? No, just put it in the object. And you sort of have to say that over and over again. And finally, the guy would go, oh, you mean I can just put it in the object? But this is going to be easier than SQL. Yeah, because it really is.
Been doing this for 20 years, right?
Right, and so yeah, we're still seeing that, and that's the reason I'm still out there talking about it. Is you go to an ad tech company, and this is obvious, right? I mean, duh, you're going to keep the behavior, and you've got a cookie, and you're going to go look it up. You're going to have a list, and you're going to use it for a behavioral thing. They would never try to take a SQL-style approach. But we believe, and I see the cases where there's a lot of faster-moving algorithms for which this is a more appropriate solution than a SQL solution. And you asked about competitors?
Yes.
So within the key-value space, we find that AeroSpike has few competitors. I've mentioned Cassandra. We see that in the key-value space still. And are able to provide pretty strong lower cost of ownership for it. We see a little bit of Redis now and then, but it's scaling, difficulty in scaling. Nothing's impossible to scale, but difficulty in scaling is a reason people will choose AeroSpike instead. We also see in-house inbuilt solutions. So if you're looking at the security industry, let's say FireEye or something like that, they've mostly rolled their own, and they don't use outside technology for this layer, but they do have a layer like this. You can even look at systems like Splunk. They'll have inbuilt systems, even though they're not using as much streaming style systems. So we see a lot of people who are thinking, well, wait a minute, I've got this thing that my CTO built 4 years ago. Maybe it's time to switch to something more better supported and used by multiple customers.
Thank you.
I guess one reason why NoSQL probably is more popular or more prevalent is because of the fact that both RAM and storage is much, much cheaper. And this is less storage efficient, right? It's much faster but less storage efficient compared to SQL.
True in a way, because it's not like Oracle doesn't have a few tricks up their sleeve within memory. And they don't have two different in-memory solutions, both coherence and times 10, that have been in-memory solutions for at least a decade. So even from the old line providers, we have essentially NoSQL solutions. I remember I presented AeroSpike to a guy in New York at JP Morgan, and he basically accused me of reinventing IMS FastPath, which frankly I take as a great compliment. That's one of the most wonderful, reliable databases on the planet. But NoSQL can be seen as really, I would think, a next generation compared to some of those systems. Going to Oracle's Exadata is flash optimized, right? The tricks that they've done in there, I know through a friend of a friend, some of the person who's done it, I've read their PhD thesis, and it looks a heck of a lot like the internals of AeroSpike. So it's not exactly like they are really, they do what they can, but there's really a lot of layers, and we've done some simplification.
To doing the queries into a list. Is that a typo there? Is it 4.27 then it should be? The net 2 should...
This one here?
Right. So I'm trying to figure out how that works. Net 1 gives you a range of IP addresses.
This should be a 17.0.
Okay.
Sorry, yeah, these two numbers are just wrong.
Okay. All right. Okay.
Completely wrong. I don't know what I was thinking. Actually, no. I was actually, these are two overlapping networks. right? So normally, and I was trying to make actually a point about, normally you wouldn't have a 4.7, but even if you have a case where you have overlapping networks, and let's say you have in fact determined that there's a unusual network range, because you could argue that using a proper range index like this really gets you all of the different strange network addresses, right? So if you use a where clause, you'll get everything, even in the case of weird networks. So the point, trying to translate that and make it sort of a featureful comparison, even in that case where you looks like you would want to do a range query to get a kind of weird overlapping number, you would say, well, no, actually, things in 4.0, this has a component of 4.0 and this has a component of 4.0. Therefore, these networks belong here. They do belong here, actually, because this, the typo really is this one should include net 2. So that's the mistake. This should include network 2. But the goal is to map arbitrary network ranges to a query, even though you may have to throw some stuff out and stuff like that. You may actually end up pulling more data. Yes, in the back.
A very generic question. Actually, I recently going through the graph database, that is Neo4j. I read they are also doing fraud detection. And if I'm not wrong, 3 companies already implemented. So how do we see, I mean, Aerospike is going to be different compared to Neo4j, or
Sure.
basically don't compare the graph database and key value other than that.
I like Neo4j. Emil's a great guy. He lives over in Menlo Park near me, and we meet for coffee sometime. So I think Neo4j is great, for the record. So what's interesting about this paradigm is a scalable storage system under any computation concept. So if you know your problem is a graph problem, go use a graph database. What we're finding in fraud is, well, some of them are graphs, but some of them are ML constructs. And how you map an ML construct into a graph is far less clear. An ML construct is going to end up something a lot more like a sparse matrix math problem. And sparse matrices are best done as essentially sparse vectors with key value lookups. You can build a graph-like system with a key value system. You just need a graph database on top of it. And in fact, I talked to Emil one day about, hey, what about if we actually take some of your processing systems and underlay Aerospike as a storage engine? I still think it would be a really cool idea. We've got it as a, maybe we would end up doing it someday. But they end up having their own storage system that's more highly optimized, and that's cool. So that, I think, is the difference, is with a key value system and any application, you could build graph-style exploration algorithms. You could build ML. It's going to be a little more general purpose, and it might even be slower than using a special purpose graph. On the other hand, you're going to be able to cover more algorithms with the same system instead of having to have a graph DB and also something like us. One more question.
Yeah, no, I don't have a question, but I hope we will show up on your 3rd page from the last there soon, because we have a new product coming out with the all-flash array storage, which will enable and answer some of the questions you had over there, where you can basically achieve better performance. It looks like one flash, but it's really a virtual flash outside in an array. And there are many benefits with that. Hopefully.
Would you like to say the name of your company?
we call it Parent Data Systems. So we're working on a flash product. We're basically going to start beta testing here in December and go forward from that. So hopefully you'll see our name coming up here pretty big next year.
Absolutely. We've worked with Aperion for a while, Aperon for a while. There's a lot of interesting work happening in Flash. And just like, this is probably, maybe I should have put that on the slide, but we're sort of in this NVMe phase right now of NAND flash goes to NVMe. But there's this really interesting set of work happening in, the storage guys call them all flash arrays, but we just like to think of them as storage, and maybe they will end up solving some of these QoS problems. We keep working on it and hoping it. I did take out my slide about storage class memory. I should probably put that one back into the slide deck. If you guys have followed the Intel X-Point announcement recently, that stuff is really, really, really interesting and capable of much higher speeds with an upcharge, but not with a lot of upcharge. So we've been working with Intel diligently and some of the other providers to fit X-point and different kind of resistive memory technologies into our database as well. It's fascinating stuff. Okay, so thanks for coming out. Feel free to hang out and have another beer.